today's session. It's my pleasure to introduce Florian Pop from Penn University, who will talk on the birational and p-adic section conjecture.
Yes, sir. So first I would like to thank the organizers for giving me the opportunity to speak at this introductory workshop. And actually I have to say I changed my mind a few times. The first time was that actually my talk was supposed to be a little bit more introductory, but after seeing the talks and during the first 2 days I realized no way, and maybe with 1 or 2 exceptions. And then second, I want to give a talk with technology, but as usually technology wins, and therefore I have now here the slides. And okay, that means I will give a human talk. Okay, so maybe here the title on birational p-adic section conjecture. Okay. And the first part of the talk is to give some motivation and notations. Motivation introduction. And I will start actually what Thomas Samueli did 2 days ago is very helpful, but I will make a little bit the things more specific because I'm going to speak about the birational section conjecture. So what is the section conjecture? First, just take K any base field and maybe X any first smooth connected curve, geometrically connected curve over K, and most of the sessions do not have to do with curves. And then you have maybe you have this exact sequence which was also in Samueli's talk, where I neglect base points. I will tell you why. And here GK. Well, this is the étale fundamental group, and this is the so-called algebraic fundamental group of X. And then maybe I should say here further, and let X0 be then smooth completion. Now here I already said I have a little bit of fun, because if you have a smooth geometrically connected curve, it doesn't necessarily have a smooth completion, but let's say that it has smooth completion. Then you have the following situation. So, and now you take a point X in a K rational point of the completion, then you have the following. So first, if X is in X of K, then sorry. Where is the eraser? Under the here, lots of erasers. Maybe I will do something more here. Yes. Now I draw the picture, the geometric picture for this. Actually, this gives you, let's say, X tilde to X be the universal cover. But in a étale sense, that means this is the normalization of X in the, well, it's a projective limit of all the finite connected étale covers. And this is then a scheme over K, and it's not a finite type, but anyhow one can speak about this. And in particular, if you have such a point X in K, then you can choose a point X over X, well, pre-image in X tilde, and then you have the following picture for this. You can define the inertia of X tilde over X, normal subgroup in the decomposition group of X tilde over X, and this is everything in pi 1 of X. Okay, and you have an exact sequence of the following form. 1 goes to the inertia, decomposition, GK, And it's essential that actually the point is rational. In general, if the point is not rational, then you have to put here the absolute Galois group of the residue field. And now you have then the following facts. So if x is already in x of k, then the inertia is trivial. Hence, the decomposition group is isomorphic to the Galois group, the residue field. And in particular, this gives you a splitting, yes? Hence, there exist Sx splittings of sections of this projection, maybe, which we call sections above x. Yeah, so this is essential above x. And because I work in this, well, so you see that actually, so all the points above x, all such points are conjugated under the, actually under pi 1 of x bar, and that means these sections are all conjugated under the geometric part of the fundamental group. And now what happens if x is in x0 of k, but not in x of k? So this is a cuspidal, yeah? Cuspidal point of x. Well, then you have exactly the same picture further on, but then usually this is not trivial. And then again, this is always split exact. Split exact. And then you have lots of sections, yeah? Lots of sections Sx above x, which are classified by the non-commutative H1 GK. Yeah. This is just a pointed set. Okay, now maybe a remark. So a few remarks. First, if characteristic of k is 0, then so then in the case B, and in B, one has I x tilde over x is always isomorphic to z hat 1. And in particular, this is a group. And in particular, H1 GK Ix tilde over x is, via Kuma theory, isomorphic to the at the completion of k, so we understand very well all the sections. Yeah. But so first, now if characteristic of k is positive, well then this usually, so H1 of GKIX tilde over x is, I would say, only huge. And we have no description of this guy here so far. Okay. Now, what is, so I have to check where I am here. Yeah, so what is now the section conjecture? Now we consider the following situation. So now let be x hyperbolic. So please ask if you have anything, any questions. Hyperbolic curve. Now this is by definition a curve with Euler characteristics, Euler characteristic negative, and in particular for that, well, I will say part of the definition is also that actually it has a smooth completion, yes? And then the section conjecture is so the classical section conjecture is the following. So let x, so k finitely generated, infinite, and x over k hyperbolic non-constant curve. Non-constant means only that actually if k has positive characteristic, then X should be not defined over the algebraic closure of a finite field, yeah, then all the sections of this canonical projection arise in the ways described above. Arise from X in X0 K as described above. Ah, yes. So, well, maybe, okay, up to pure, thank you, inseparable base changes. Okay. Well, I say covers or something like this. Yeah. Okay. So this is the conjecture, and yes. I did not. So why is it split? Yes. So it follows from, yeah, so maybe actually one has, so in the positive, there is no simple reason why it is split in positive characteristic. Okay. But the reason is that actually it is split even if you go to the birational form of it, which I'm going to explain now. Yeah. Okay. Now, so this was the initial section conjecture, and then the people tried hard to prove it, and we have no idea how to do it. And there is evidence for this, which I would mention maybe something like Nakamura's results concerning cuspidal sections and Tamagawa's conditional section conjecture over finite fields. So he gave simply a condition on sections which is of pure group theoretical nature in order to come from points. And then there is work by Mochizuki, which does also describe so that some sections come from points in the p-adic setting, and there are results concerning variants of this, about where you replace pi by motivic pi and so on and so forth. Yeah, so, but so far the section conjecture in this form is completely open. Okay, now maybe I should see here variants of this. So the first one is maybe replace K by local fields. Yes, e.g. K over QP finite. And then what you get is the so-called p-adic section conjecture. P-adic or local section conjecture. And then replace, well, let's put it like this. So take limits. Take limits over a system of open neighborhoods xi in x0 of the generic point of x. And what does it mean? Id est replace pi 1x by the absolute Galois group of the function field of x. And then what do you get? And get 1 goes into the geometric part of the absolute Galois group. This is k bar of x, not of x bar, and goes in gkx. gk goes to 1. And then you can ask exactly the same questions then by functoriality of the construction above. Get if you have a point x in x0 of k, then this guy gives somehow a section. Well, and you have what? And you have now a point x, well, I will not. Then from this you get many sections S defined on, well, let's call it, I don't know, S bar maybe. GK with values in GK of X, yeah? Section of per X. I put here kappa of X, yeah? Section. Yeah, so this is, but everything is, it is true also for non-curves, but for curves, yeah? Okay, now how do you get sections? So now this would answer your question. So the point is that there is something, this is a theorem about valuation theory, that if you have any valuation of a field, so this is maybe general fact, just take any field omega together with a valuation v, and take the decomposition group of v, a decomposition group of v. So that means now you, okay, so picture omega v, then omega separable closed vs, some prolongation. Then for this you can define the inertia group, the decomposition is like usual, and then you get the exact sequence. And so here is simply the residue field of V. Yes. And the point is that this is always split, yeah? Is always split. And why is it so? So one has a nice description of this guy, and so, but so actually, well, why is it so? So you have here I bar V over V, which is the maximal tame quotient, d bar over V, gk of x, gk of V, and here is equality. Again, projection. What is the kernel here? It's the wild ramification group. And the point is, this is well known, this is an abelian group, and so if the valuation is discrete, then we know what it is. So this is z hat modulo zp1. So if V is discrete, yeah? So if V discrete. And if it is not discrete, then it has a similar description. But anyhow, this is very easily seen that this is split. And after this, now you have to split this exact sequence. And now what is the point? If the characteristic, this is a pro-P group, the only problem is can come from the P cohomology of this group. But if the characteristic is positive, then the P cohomology is the higher, well, this is cohomologically not trivial, but H2 is trivial. Therefore, there are no obstructions for extensions, and this is actually the explanation. And I don't see any geometric reason why it is so. But, well, no, no way. Actually, this is actually the complexity of P extensions in positive characteristic. So the tame part is fine, because by the Abianca's lemma, when you make something divisible, the inertia disappears. But not so with P. Okay. So, please. Yes, you can put R, but R is way too little. And there was in Kirsten's talk yesterday something that actually what sections C are connected components of. So in this case, the real points of the curve is by Hadamard's theorem is a connection, is a union of circles, at most G+1. And what the sections C are these connected components, these circles, but not more. Yeah, so the real is too small. Yeah. Okay. Now let me move on. So. Yes, and the p-adic, okay. The conclusion should be exactly the same. This is actually our hope. Okay. Now, I should say maybe that here, so maybe before I move on. So I mentioned some facts before, but so there is a fact actually, the p-adic, so birational p-adic section conjecture is true. And this is by a result by Königsmann. I think it was maybe around 2004 or 5, something like that, yes. And now I come now to the, so that is the introduction and so on, and I come now to what I want to say myself. So new results about birational p-adic section conjecture. So actually you can ask what new results, because we already know the section conjecture is true. Well, the point is that this is somehow a very wild assertion, yeah. So it means you are not happy because you have such a huge Galois information in order to prove that the section conjecture is true, and you would like to prove it at a minimal, with minimal information. So and I would, so this is a kind of minimalistic birational p-adic section conjecture. So this is actually the subtitle of what I'm going to tell you. And to be honest, I say maybe that I was surprised that this minimalistic section conjecture is true. And I should say, 2 years ago, something like this, maybe more, 2 years ago, we had a conference at Penn about Galois theory and all kinds of section conjecture, birational aspect, I mean unabelian aspects of, and with the, so Königsmann explained his result there and so on, and what is that? Ellenberg, yes, Jordan Ellenberg. He said that actually one should not believe that the section conjecture could be under too minimalistic hypothesis. And that was for me somehow a kind of, now let's see how minimalistic can it become in order to be true. And the truth is that actually everybody, so I was surprised and others too, that actually one has such a minimalistic factor. Okay, now what is the notations for this? I start with k over qp some finite extension, which contains the pth roots of unity, and then x0 over k is some smooth, well, complete geometrically connected smooth curve. And the rest of the notation are as before, so you k should be the function field of x0. And you do the following. Now let be k dashed over k be the maximal z mod p abelian elementary extension. What is this? This is k dashed is simply k adjoint pth root of all the elements of k, yes? And then you repeat the step once again over k dash should be again maximal zp extension. That means what is k double dashed? Well, it's k dashed pth root of k dash. Now, what is interesting about this is actually you really can write down these things, yeah? So, and do the same with k dashed over k, and maybe k double dashed over k. Yes, and can I write here? Oh, yeah. So, remark, maybe I should also then put here the canonical projection. So, the Galois group of k dashed over k. And in the same way, the projection double dashed. Galois group of k double dashed over k. And okay, so what is this? I would call this the maximal Z mod P meta-abelian extension of K, and in the same way, this is the maximal Z mod P extension. Now, remark
You want to write K double dash over K dash.
over K dash. So, thank you. So, it's, well, it's maybe just an exercise that this is Galois over K and so on and so forth. Okay. Now, then you have a diagram which I'm going to leave it at the blackboard like this. Maybe I put the diagram here. So you have Galois K double dashed over K, Galois K dashed over K, then yeah, so all these are, so it's a commutative diagram. And what do I want to say is that actually these guys are really known, yeah? So note G K dashed, maybe even, yeah, so K dashed over K, this is by class field theory very clear what it is. And also K dashed over K, finite known, yes? Or I say well-known extensions, okay? And now the result I want to tell you is the following. So I would say that maybe none of the assertions is obvious, but looking at this diagram there. So now the result is, so theorem in the above notations. The following hold. So 1, every rational point of K rational point of x0 gives rise to, well, to a bouquet. Yeah. So let's call it, this is a nice word. Bouquet of sections above x, sections S x defined on, sorry, okay, sorry, fine. Now here I have to introduce, to say something more. I have to define before I, okay, now I have these projections here, and maybe you can imagine that this projection might have lots of sections, and this projection might have lots of sections, and every section here, I think it's almost obvious that every section here will give you a section here, yeah, by functoriality of, because what is this? This is just this modulo the commutator, yes. And but there are maybe lots of sections here which do not come from sections here, yes. And now I will call a section here which can be lifted to a section here liftable, yeah. So S dashed section of is called liftable if there exists S double dashed section of lifting it, yeah, it to, yeah, okay. Now, so the assertion of the theorem is that every k rational points gives rise to a bouquet of liftable sections Sx of k dashed above x. That means above x they arise in this way which was explained here before. And this is maybe not so surprising because of the functoriality of all the constructions here, but maybe the most surprising fact is that every liftable section comes from a point.
Are you saying that there's a map from sections of PRK times to sections of PRK?
Yes. So it's because it's functorial. Let's just say, actually, all these constructions, the group theorists call these things like taking quotients by the commutator and so on, verbal construction in groups. All these verbal constructions behave very nicely functorially and so on. That means, indeed, every section from here gives you a section there. But there are lots of sections here giving the same section. But not every section here is liftable, as the theorem says. So conversely, every liftable section S of is defined, well, comes from a point x, x0, k, as above, as described above. Okay. From a unique. From a unique, thank you. From a unique point.
And the bouquet is parameterized by each one position.
Yes. Yeah. So, and this is above x bouquet, which is h1 g k dash over k and z mod p. But you see that actually, because the action is trivial, because we said that the roots of unity are there, this is simply homo. So this is the size of the bouquet. It's exactly homo. Yeah. And conversely, now, I do not know, for me this is really a very minimalistic form of the section birational section conjecture. And actually you can make it even more minimalistic, but it would be too technical. Maybe Mohammed will say something in his talk. And yeah, so one question is what to do if you do not have this situation. What are my hypotheses? What are my hypotheses? Mu p in k. Then, so what to do if? What about mu p not contained in k? Then we know, so the picture is complete also then. So then maybe A. If mu p is not contained in k, then there exist many more liftable sections than points. Then there exist many more liftable sections than points.
What is the definition of H1?
Well, so then it's again, you can take again the maximal abelian extension, then the maximal z mod p meta abelian extension. Yeah. Okay. And now what is the reason for that? Well, if mu p is not in k, then this guy, then the maximal pro p quotient of the absolute Galois group of little k is pro p free. This is one of the things which the people know. And in particular, there are no obstructions for splitting this. Well, there are no obstructions if you go up to the maximal pro p quotients. And now you will say, well, but even then there could be enough. So even then every section could come from a point. Well, the problem, you can start with a curve which has no points, but has lots and lots of sections. So there is no way that actually. And B, now what to do if what is there? Can one do something? Well, one can do the following. So let now L over QP be arbitrary. And you take K over QP finite Galois with L in K. L in K and mu P in K. And then if you start maybe with Y0 over L as a, complete geometrical integral smooth. Then you set x0 should be the base change of y0, okay? And then do the same, large K equals then kappa of x0 and so on. And do exactly the same construction which you did before, and then you check that these, so then you have a diagram like this then. So then you will have g k dashed over, maybe I should say here, and you set L should be L of y0, so function field of L. Then the point is that this, you have this commutative diagram. And in the same way, you can speak about sections. So now this is projection L. This is projection little l. Maybe I'd drawn the diagram in the different. Sorry. And this is. Okay, now it's correct. And then you have here double L, and these are the canonical projections. And then you define in the same way a liftable section here, and so on and so forth. Exactly the same result is true. And this is more or less a formal consequence of the first result. Yeah. Okay. Maybe I will only say then. Yeah. Then the theorem is that exactly as above, so 1 x in, or maybe y now, in y0L produce bouquet of liftable sections S S dashed of the projection L dashed, and that bouquet is exactly as before. It is H1 gal K dashed over L now, and now I have to say Z mod P1, because maybe the Galois action is not, and then this is a true bouquet. This is not a so it's a group again, but it's not home. And second, conversely, S section of Pru L, liftable section, sorry. Comes from some y0 in y0L. Okay, so this is the complete picture of what happens when the roots of unity are not there. So the assertions in the initial form are not true, but if you improve it a little bit, then you get this. Okay, now maybe I should give some maybe consequences or applications. And the first observation is that naturally this theorem prime implies the p-adic, the birational p-adic section conjecture. And why? So you can take limits in two ways. You start with some curve like this, and now you let enlarge the. You take bigger and bigger extensions, k, finite Galois extensions, and you do this. And in the same way, you take covers of y in such a way that you somehow exhaust the whole, the corresponding function fields exhaust the separable, the algebraic closure of the function field of y. And everything is here functorial. So lift comes from a unique again, from A unique. And because of uniqueness and functoriality and so on, finally you get that the section conjecture. Now second, it also gives something about the section conjecture for curves. So a kind of, so let x now over k, well, I should, maybe the context is like y0, yeah? So y over L be a smooth, well, smooth, geometrically connected curve. And then what do we want? We would like to have to prove the section conjecture over this, yeah? So here, L over QP finite. Then the assertion is then there exist finitely many Z mod geometrically. Z mod L abelian covers elementary abelian. Z mod P, thank you. Abelian covers yi goes to y0 such that, first of all, I call it maybe phi I, yeah? Phi I of yi of L union over. No, so this could be ramified. I don't say unramified, yes. So union over I of phi I of yi of L equals y0 of L. What does it mean? So every L rational point of y survives in at least one of these covers. And second, if S defined on, if S is section of phi 1 of y0 goes to GL, which survives in at least one of these covers, yeah, which lifts to some section, to a section of pi 1 GL, then these sections come from a point. Then S comes from a point, from some y0 in y0L. That means we cannot prove the section conjecture for L, but for everything. So, and this family is effectively computable, and so on and so forth. So you know precisely what you are doing, and if you have a section which survives in at least one of these covers, that means you have to have the picture. Yeah? So you have y. Here's L. That will give you a picture pi 1 I, pi 1 y0, GL. And now you have a section here, S. If you succeed to lift the section to at least one SI, then that section must come from a point. And you see that actually it is if and only if. Yeah? If a section comes from a point because that point survives in one of the yi, that will be liftable. Yeah?
You have some freedom in choosing field K.
You have a lot of freedom. You have a lot of freedom. You can choose K to be any finite Galois extension containing the p-throughs of unity.
And then H1 of Galois K prime over L may change. But the right, the left-hand side you have this point of y0 of L.
So the H1 will not change. Exactly, this is what this says. Yeah, the H1 will not change. Yeah. So if you change x, then okay. So maybe I should. Yeah. Okay, so this is another application, and maybe a second application for which actually I would have to give a little bit another variant of the theorem, which is nevertheless true, and this is actually what is proved, is concerning adelic points. So, and I will tell you only in words how you have to modify the assertion of the theorem in order to make it work. So imagine, there I said, you start with k, and what was k? K was over qp finite. But you don't have to start with a k which is qp finite, you just have to start with this and then replace k by a k0 in k relatively algebraically closed. And start with a curve defined over k0 and take the function field of that, take that maximal pro p extension and so on, and then the assertion takes place exactly in the same way. The sections at this level come exactly from the k rational points of the curve. Now, using that, you have the following for the application. So maybe let now be k a number field and x over k as above. Yeah, and as defined on phi off, as defined on yeah, so number field as above. Yeah, okay, sorry. And take now S defined on gk into g kappa of x section. Yeah. Then x of ak is non-empty. That means if you have sections of the canonical projection section of maybe bar k defined on the absolute Galois group of kx with values in gk. Now here you see that actually you have really the full Galois group, because how you put this together, you could take the maximal. You don't have, you need for this only the nilpotent order 2, so nilpotence or degree 2 quotient of the absolute Galois group, but anyhow, so I don't want to make it too technical. But the final point is that if you have sections in the birational setting for curves over function fields, then the curves have adelic points. The converse is not true, unfortunately. Well, to have sections is much more than having an adelic point. But anyhow, so this is a...
Being adelic point is the same as the point of each place.
Yes, yeah, more or less. And now next, so thank you. This is a very subtle question, because what did I say all over here? I said all the time, well, how would you do this? You restrict to the decomposition groups of places and apply this machinery, and they will give you a unique point from which the section comes. And now the question is, what happens if you take these points? Are these adelic points? And we do not know. And I think that maybe one of the big steps in proving the conjecture, the section conjecture, is to prove first that if you take these unique points, which are given by the local theory, they really build an adelic point. So far, until now, these points could be very bad at every place. The bigger the p becomes, the bigger the denominators could be in there. No. So the point is, well, the section, so the problem comes from actually from cuspidal sections, and you could have something which is not complete. Yeah, you could have, now x is affine, and you have a point in the at infinity, which then grows and becomes very, very bad. And I think that actually, I don't know, so this is somehow related to the Brown-Mannion obstruction and maybe to the Skorobogatov conjecture and so on. I think that this could be a strategy to prove the section conjecture, namely to prove the Skorobogatov conjecture, and then to really show that here the points which you really get canonically are not bad. Yeah, and then you would get the birational section conjecture. Okay. So I don't. Sorry.
So how do you get the adelic point?
So the adelic point is there are anyhow at almost all the places there are points. We know this, yeah, because of the veil bounds, the the curve it has a good reduction almost everywhere. There are only few, there are only finite number of places where there are problems, and those are taken care of. And there you have the canonical thing. Okay, fine. And maybe I don't want, so this is a direct consequence of this. Actually, this is not a direct consequence of this, and you have to look into a little bit more careful at the situation, what happens and so on, and is related to the fact that by this you can prove that your sections avoid the so-called peak part of H of here,
For this
H2.
statement, wouldn't you get away with the zero of those, no? Do you need your sharpened form for this? For this corollary 3?
No, never, no, you can't do anything with this theorem by Königsmark because you have to have the whole Galois information.
But you can state the stronger state.
But
in
you
three.
stated the whole Galois information.
Yeah.
But three is true even if you consider sections of the geometry to be meta-abelian. Absolutely.
Yes, that's the point. Actually, what I wanted to say is you can replace this guy by a much smaller thing, which I would call, I don't know. Yeah, so on.
But I can repeat my question. So if you
Yeah.
get only this with the full Galois group, then you get...
I think that follows, yeah, if with the full Galois group follows not exactly from the birational section conjecture for p-adic, but from forms of it. Yeah. Okay. So what I wanted to say here that actually one of the points here is so you look at h to x maybe z mod m1, and then this has a peak part, namely peak modulo m, and it has the Brouwer group, so it sits in an exact sequence, the peak part and peak zero part, and the Brouwer group of x. And what you really have to show is that when you have sections, where from do come all the problems? The problems come from the fact that actually sections could hit the peak part, and because of this, you can choose these covers exactly in such a way to ensure that the section do not hit the peak part. Yeah, and this is actually what. Okay. Now I have only 6 minutes left, and I wanted to say something about the proofs, and I could do that now with slides if I would know how to work with the machine. Yeah, I have only 2 slides for the. Okay, but then so then I simply write down. So now 3 proofs. So what is the situation? The situation is like this. I have here k, and I have here k dashed, and here's little k dashed. Maybe here is k dashed. And what is the point? So the point is I have here k dashed. And now I have a section of this that means, what do I? So k dashed is now m together with, so this is the fixed field m equals k dashed fixed under the image of a section. Yes. And then I have something, so this is huge, a huge extension. Then I have here k dashed, and this is such a diagram, yes? And what I want first is, so this is the picture which comes from a section S dashed, so S dashed section of okay, and the first lemma is, which I call it maybe lemma 0, is that under our notations it follows that the Brouwer group of so only, let's say, the p part, so the p torsion of the Brauer group of K goes injectively into the p torsion Brauer group of M. And now we know the Brauer group, the p torsion in the Brauer group of K, so this is generated by maybe a cyclic algebra. Let's call it epsilon pi with a root of unity of order p. And more or less this says that actually when I look at this and I look everything over M, because of I would say maybe this is it's an exercise, but if you have a student which does it as a homework, then he is very good. Yeah. Actually, I think that maybe there is no very good student who could do it without learning a lot before. Yeah, okay, but so this is the lemma 0. And now you have the following situation. So K is a function field of a curve over a p-adic field. This is the fixed field of the extension, and you know that this algebra over this M is non-zero. And now the big question is in all this story is, and this is how should I call it? Maybe this is the evergreen of the abelian of an abelian geometry. Where do you get points from? Yeah, so where do you get points from? And the one answer is, and this question actually in one form or the other was answered when solving, when proving results in an abelian geometry so in the birational setting, curve setting, and so on. So, and here is where do you get points from? So this is the local, so the Tate, Roquette, Lichtenbaum local global principal for Brauer group of X0. Because of time, so I will not say what that is, but this is more or less a duality theorem. It's the duality between between H0, well, between the Jacobian of the k rational points of the Jacobian and H1 of X, H1 of GK with values in in k rational points of the Jacobian. Yes, and so I will not say more about this. Yeah, fine. And the question is then, so what is the, from this you would like to have somehow a kind of local global principle for this M. So this is more or less this local for the Brauer group of X actually gives you a local global principle for the Brauer group of K. Because what is Brauer group of X0 is the unramified part of K. So the ramified part take care of all the localizations of X at the close points of the generic fiber, and this has to do with some other kind of localizations. Yeah, and now the question is, you would like to have, but you see, it has to do with some kind of points. The question is, what kind of local global principle could hold for M? Now the naive approach would be, so you have K, so this is the function field of X. Now you have M, which is a huge Galois extension, and why not? Maybe you denote curly X normalization of X in M. And at least this is how it works for number fields. For number fields, if X is spec of OK, and K is a number field, then, and you take any extension of a number field, then the Brauer group of that has a local global principle of exactly the same shape as the Brauer group of X. You just prolong all the valuations from K to M, and you get local group. And the point is, if you do the same here, things do not work, and you don't have a local global principle. And the answer is, let's denote maybe X V to be the set of all the prolongations of V. So V prolongation of V equals Vk. So this is the p-adic valuation of K to M. Well, this is a horrible, well, this is a horrible set of valuations. Some of them have nice geometric interpretations, but most of them do not have any geometric interpretation. So among these are, if you take for x any model, normal model over the evaluation ring of K, then when you localize at the generic points of the special fiber, those are here. So these have a nice geometric interpretation. The other kind of evaluations here are, you take a closed point of any closed point of x, the residue field is a finite extension of K. Now this residue field has a unique extension, on that there is a unique extension of the canonic valuation of K, and you compose the two valuations and you get something which is, which the Russian school calls a two-dimensional local field, a multi-dimensional, two-dimensional local field. But there are other very horrible valuations which you have to take into account. The only good news about this is that this is compact in the patch topology. And the second very good news about this is the following. There exists, and so this was proved many years ago in my thesis. So there is a local global principle of the form 0 goes into Brouwer group of M, goes into direct product V in XV M, and now you take W, and you have to Henselize not to complete because these guys are also of rank 2 and so on. So you have such a, and now if you have a lot of fantasy, then you can believe that these are points of in some space. And then the whole problem is, okay, I have these points in this space, which is some strange space. But by the way, so this has really a very nice interpretation. I could write it down. So this is exactly, so this as a set is the projective limit over all xi, where xi are all possible normal projective models of x over the valuation ring of K. So these build a projective system. Any two can be dominated by others. You could take them even regular and so on. And if you take the projective limit of that as a set, turns out that the projective limit as a set is this. Now you can also put some structure on this because all these have nice algebraic structure, but it's a kind of valuation space, yeah. Okay, so that is a geometric interpretation of this. But as I said, so there are lots of bad points there. Okay, but anyhow, that is a set of points. And now your hope is that knowing what? Knowing lemma 0, the Brouwer group of M, this algebra survives in the Brouwer group of M. Apply this local global principle. There is a W where that algebra survives. And if you are trustful in the future, you say, this valuation must be unique, and this comes from the point I'm looking for. And the answer is yes, you are right. But on the way, so there are so many miracles which have to do with the precise structure of the epsilon of the Galois group of P, and with results coming from the Tate-Port duality for local fields and so on and so forth. That it's really, at the end, you really have to believe in miracles to see that, to believe that actually, well, all this must happen eventually. Okay, so I will stop now.
Could you tell again which class in the Brouwer group of K you take to...
So that is really, so the P torsion in the Brouwer group of K is by local class field theory. So this is isomorphic by the invariant to Z mod P. And you really have to work with in order to do all these computations and to see that everything works, then you take so K has a unique unramified extension of, well, maybe K1, a unique unramified extension of degree P. And this, so now you will have the algebra K1 and pi and Frobenius, yes. Frobenius. So, and you have to work with this algebra because on the way, as I said, now you are here in this huge guy. The only what you know about that is that when I Henselize at some prolongation of the valuation, this algebra is not trivial. And now you play a lot of acrobatic and so on, acrobatics, and then eventually you realize the only possibility for this valuation is that it is, if it is not of this type, yes, you have the valuation decay here, and then you compose with the valuation of a closed point x0. So if you are in this situation, then it's fine. So the valuation, so your section comes from a point. But suppose that is not this, then the only possibility for V is that it is a discrete valuation with finite residue field. This is what you finally prove. That means, well, but then this is a prolongation of Vk. This is also a discrete valuation finite residue field. Therefore, this guy must be finite over K. And after that, you look at the precise structure of the Galois groups of local fields, of p-adic fields, and realize if this happens, that this class does survive in a finite extension, then again some miracles must happen. And
You did not explain where liftable is used.
so liftable is used actually only at this place, in lemma 0. This is the exercise which I said.
Oh, that's
Yeah.
an
Sure that the probability of K survived.
only
Is this only there? All and this kind of assertions here are after that very general. You just must have a valuation of rank 1. You don't need. You just must have a valuation of rank 1. Residue field P, characteristic. The field should be characteristic 0, and well, more or less you have an axiomatic proof of what's going on here. You have an axiomatization of what you need, and it turns out the only possibility for such things that you are discussing about discrete valued fields with finite residue.
Questions?
Sorry. Your initial local global principle really requires all valuations, I guess, right?
Yes, yes. And one can prove if you leave one out, but in such a way that the cohomological dimension of this guy is bigger than 1, you lose. You really have to take all of them. Actually, I thought a lot along these lines, because what is amazing, eventually, this guy has a point which sits about, but there is no way that you can see this point by taking limits or doing some. Actually, it would be interesting to have another construction. But
I'm a little confused about how this theorem prime is going to imply the birational p-adic section conjecture, because it seems like the only extensions that we're dealing with are extensions that are somehow combinations of base field extensions and elementary p extensions, and so that we're not. So how are we getting the entire Galois group of K?
So
can we just do that, or?
Yeah, so you also take covers of this, which are geometric. So what you do is take a section. Now take all the open neighborhoods of the sections. Every such open neighborhood is a function field. So the fixed field is a function for one variable over, again, L, because of clear reasons. And now you take, so that means you will have for every such open U containing the image of S, you will have a curve YU covering your Y0. And everything is defined over L. Yes? And it's in such a way that actually in the Galois group of this guy, the section survives. But then, now for this, you do the whole construction, what do you get? The section at this level comes from a unique L rational point of YU. Now, because of the uniqueness, that must map to that point, rational point of Y. And because of the functoriality, you get a sequence of rational points and so on, and those define your section. Yeah, that's right.
I mean, do you know what K you would get? I mean, if you tried to do this for, say, K, you start with lifting the projection prime to, say, K triple prime, or something like that. I mean, what would this section?
So, actually, I thought about this a little bit. And maybe, actually, the obvious answer is that then the sections at the second level are unique and define already come from points from there. I think that, but I can't prove. I also did not give a lot of thoughts to this, but I can't prove it. And actually, maybe yes, because you asked it, so maybe better result would be not the Z mod P meta abelian, but the Z mod P abelian bicentral. That means Z mod P nilpotent of order 2. But for that, I cannot prove this. Actually, this is really the only place where you use liftable. And I asked many people, but I don't see how to prove it. So you could make some very technical assertion, for instance, geometrically. I think that it's enough geometrically nilpotent of order 2. Yeah, that means, but yeah, I thought, okay, so eventually one has to write down something and move on. Yeah, but you are so well. There is this philosophy that actually the whole lambda ring of every field is encoded in the maximal nilpotent of order 2. Yeah, for every L different from the characteristic. This is now because of the Voevodsky, or because of the generalized Milnor conjecture. And for P is 2, P equals 2, this is exactly the Milnor conjecture. And therefore the philosophy is that everything should be seen at this level, maybe meta-abelian, well, definitely meta-abelian, but maybe even lower, namely nilpotent level 2.